Hello and welcome. In this video, we're going to simulate a buck converter that is designed by a microchip. So let's go to the menu, choose simulate. And if you don't have this, you need to install it by going to your profile, extensions and updates, then choose the mixed simulation extension. Install that and restart your computer. So once that's done, go to simulate, place simulation generic components or devices. Now the buck converter is a switch mode power supply that steps down an input voltage down to some lower output voltage through pulse width modulation on a switching device. So this is what we're going to build. I can do like a side-by-side thing so it's easier to view. And we'll place these parts on here. So I'm searching for a capacitor. And I'll rotate with spacebar. Place another capacitor. Escape. I'll use a power MOSFET. I'll use N channel for this one. And then diode. Could use a Schottky diode, but I'm just going to go with diode. Then we have inductor. Place that there. And let's see. Okay, so I have my input capacitor. Right. Input capacitor, output capacitor, diode. I also need some grounds and a resistor. And a DC voltage source and another source that will turn on this switching device. So to get the DC source, you want VSRC. This is a generic voltage source that supplies any kind of varying or static voltage source you want. I'm going to go ahead and expand this window down. All right. And then you use this to wire, use that icon to wire up some things, your components. Now, I made a version of this video earlier and posted it on YouTube, but it had the error in it that I want to show you without an explanation. Somebody commented, which is what I was hoping for, but it's a lot faster than I expected. Somebody commented, and it highlights an error that I ran into the first time I started trying to design a buck converter back in 2016. Okay. For this DC voltage source, this DC source here, that's good. The magnitude will set to 12 volts as per the design. The designers calculated 470 microfarad for their input capacitor. For this input pulse source, we're gonna call it VCSRC2 or VSRC2 and the pulse. Now we'll set the rise time to 10 nano and fall time to 10 nano, the period to 2.5 microseconds. Why 2.5 micro? Because that's the inverse of the switching frequency. When it says the switching frequency, that's how frequently the switch is being turned on and off. In time, that turns out to be a period of 2.5 microseconds. And then for the pulse width, that will be the duty cycle or duty ratio times the pulse period or the switching period. The duty cycle is the ratio of the output voltage over the input voltage. So this is incorrect. This is wrong with this nomenclature, but the numbers are correct. Output voltage divided by the input voltage. And really, they should have taken the forward diode drop into consideration, but this is fine enough. Close enough. This duty cycle times the switching time period is 1.04 microseconds for the on time that this switch is turned on. Now, for this capacitor, the output capacitor will be 19.5 microfarad. This is calculated in the document, so you just check the document to know how to get those values. They also calculated 12.12 microhenry for the inductor for it to handle 30% ripple of the load current. Now the load current depends on the load that's being applied. So let's go ahead and place a load. Place simulation generic component. A standard load would be like a resistor. Something simple. Rotate that with spacebar. Do a Control W to wire this part up. And then what would the load be? If the output is designed to be 5 volts and 2 amperes, we need to do 5 volts divided by 2 amperes, which is 2.5 ohms. So we want this resistor, as long as it's 2.5 ohms on a 5 volt output, it's going to pull 2 amperes of current. So let's save this. Go to Tools, Annotate Schematic quietly to rename the devices. Now you want to go to Simulation Dashboard. Now you might get a little bug where if you're working with simulations and you close them out and open them back up again, you might get this little error for the simulation dashboard. That's fine, just save, close your project, and then reopen it. So let's do that. Okay, I have reopened my project and we went to simulation dashboard. Now I can get my verification going, so start verification, and all of that checks out. For preparation, I have my voltage sources, but I want some probes. So let's add a probe for voltage on the output here. I'm going to change the color to something easy to recognize like red. I also want to see the voltage across the gate of this FET and here. This gives you a clue as to what the problem is going to be. But yeah, let's go here, place this here, right click. And yeah, that's a little strange that it doesn't, okay. Okay, good. So now we'll change this color to something bright here. Save this. Analysis setup and run. So for the transient, I want a simulation in time, which is transient, and then 1 millisecond, hit run. What do we see here? It was in the earlier video that I deleted and took down. So this is expected. When I first was working with buck converters and turning MOSFETs, I was not expecting this. Okay? And I couldn't figure out what was going on. And I spoke to my professor and he pointed out to me that this FET is on the high side of the voltage rail. So what am I talking about? Here's an application note from International Rectifier. And gate drive requirement of high side devices. This is currently a high side device. All right. Driven and full enhancement can be summarized. Gate voltage must be 10 volts to 15 volts higher than the source voltage. Being a high side switch such gate voltage would have to be higher than the rail voltage, which is frequently the highest voltage available in the system. Okay, so if you are driving this gate with respect to ground, you need to, at the very least, make sure this switch is turned way on compared to the 12 volts that's here. a very interesting, strange problem. But until we hit at least the 12-volt threshold, it may not turn on. Let's go ahead and set this to 11 volts and see what happens. So here, even at the 11 volt range or the 11 volt mark, it's still not quite at the 5 volts it needs to be. It's a full 1.5 volts lower on this output than we're needing. Let's go back in here, double click, set this to 12 volts, and then run this. Okay, it looks like it might be better, but see, still not quite there. What we really have to do is get this thing all the way up 17 volts. So 5 volts beyond the 12 volts. And now let's see what happens. And let's click on this signal. And voila, this looks more realistic because it accounts for like drops in the devices, maybe the forward diode voltage drop, which if it were accounted for in the duty cycle equation, then we would have gotten something closer to 5 volts. But this is what we are expecting, somewhere in the 4.4, 4.6 to 5 volt range for the RMS voltage, or the steady state voltage. Okay. This was the first problem that I just racked my brain with. After I eventually got past that, I was able to design my synchronous buck converter. This is 2016. Do some things in MATLAB and built it. And then I went ahead and did something a bit more involved where I use a controller to drive the synchronous buck converter to handle a switching load. And then I laid it out. This is back in the day, not just a few years ago. And then the switching circuits got a bit more complicated on the load side because I wanted to test my control. In any case, that was something that really got me. Maybe it didn't get other people, but it definitely got me when I first started getting into switch mode power supply. Okay, this is the error I wanted people to sort of try and guess, but I figured I may as well just redo the video instead of causing confusion. And here you go. Thank you so much for watching. Let us know if you've had any issues with designing switch mode power supplies in general. Okay. And also just a quick note, here we have, see this overshoot and how it settles. It takes some time to settle, right? Wouldn't it be great if it just kind of went straight up and then hit the voltage that it needed to? Or it went through what it needed to do, but it didn't have as high an overshoot or undershoot, or it settled more quickly. These are controls issues, right? So in another video, I will be doing some explanation or give a demo of this buck converter in closed loop. This is an open loop, but closed loop is much more interesting, as you see here in my design here. Okay, especially for synchronous. Now this is actually also open loop, but I do have a closed loop example here. This is one of a closed loop example. Okay, thanks again for watching, and I'll see you next time. Peace.